Hello, software engineers. Hope everyone has been having a great weekend. Here we are doing our last lecture video for the week, and this time we're going to focus on OO decompositions. Last time we talked about functional decomposition. That's a very valuable skill to have, but functional decomposition isn't going to help us when we're dealing with very, very large dynamic systems, especially when we're talking about object-oriented design, which any large complicated system is likely to adhere to. And so, with object-oriented composition, we're going to be focusing on class-based languages, object-oriented languages, Java, C Sharp, for example. Python can also be object-oriented. And it's built around the idea that we can model our problem by identifying entities, identifying what state defines the current parameters of the entities, and what behaviors those entities have interacting with each other. And we often use this to help us define the business logic of the system. So you may have seen that term before, the business logic layer. It was connecting the UI to the data layer in a three-tier architecture. The idea is the business logic layer really regulates and controls that interaction. And so this decomposition really helps lend itself to that type of system. Again, just like with functional decomposition, there isn't a right way to do it. There isn't one particular solution. If two people with the same problem statement, same requirements, sit down to design, they will likely come up with different solutions. And it's possible some are better. It's possible that they're different, but both equally valid, both equally adhering to the principles of modularity, information hiding, loose coupling, high cohesion that we want. So some general ways to do it is we can do a top-down approach. We take the big problem, we split it up into smaller problems, split it up into smaller problems, until we reach atomic objects, individual entities. Another way, though, is bottom-up, and we start with one single important object. And then from there, we build the system up around that. We define what that individual important object is allowed to interact with, and then from there we take the objects we created, what are they needing to interact with, and so on. So we don't always have to go top down. Sometimes it can make sense to go bottom up. You can also do a customer-based methodology where you start only with what the customer sees and then fill out behind it. This is, you can often think of it as like you design the UI and then build the system out from there. Kind of starting with the front end, working to the back end. It's a little bit different than top down. But again, what's important here? Well, modularity is important. What is the class? Is the class cohesive? Does it adhere to really only one particular entity and its behaviors and state? So we determine that by looking at what the methods and the fields in a class are. We also talk about how the entities interact. And we can think of this as there's a static interaction, which is to say a part of. For example, a tire is a part of a car. Whereas we can also talk about uses. For example, the driver uses the steering wheel, things like that. The driver doesn't have a steering wheel, it uses the steering wheel, if that makes sense. There's also the relationship of inheritance. An is a relationship. A car is a vehicle. A hatchback is a type of car. A cat is a mammal, etc. And then from there we can do a higher level organization. So in Java we can have packages. In Pythons we can build modules, and these will have multiple classes within them. And we want to, again, as always, when we're talking about breaking things down, think about testing and reusability. And to help us with this, a tool that helps us communicate this design choice is UML, Unified Modeling Language. And you may have seen this a bit in 2110. I know some may have seen it in SDE. But to be clear, UML is not a tool to help you design. It's a tool to help you communicate a design. So it's not designed to help you make decisions, it's designed to help you communicate those decisions. And it can be used with really almost any design methodology or decomposition. It doesn't have to be object-oriented, but there are class diagrams, which we're going to spend a bit of time on, that very much are very tightly object-oriented. And so the point of a UML is if you hand the UML diagram to a fellow engineer, they should be able to understand it and vice versa. There are several different charts. There's like 27 or something different like recognized UML diagrams. We're obviously not going to focus on all of them. There's use case diagrams, which, you know, you're identifying the actors, how they interact with the system. There's class diagrams. We're going to spend a bit of time on that. Interaction diagram sequence is one we're going to look at here in a bit. Also state and activity diagrams. And some of these are great for actually modeling the requirements. That is, some of these diagrams are designed to be able to even show to the customer. So it serves as kind of documentation to make sure that you're doing what the customer wants you to do. So like use cases, as we mentioned, you can do use case diagrams in UML. We've done some of that. There are other requirements analysis diagrams, but they aren't really used all that much, whereas use case diagram, pretty important. Another diagram is a sequence diagram. You may have seen something like this before. I feel like Jay Leno. Have you seen this? Have you heard about this? These sequence diagrams. Just walking down the street and just sequence diagram. Okay, I'm going to stop with the horrific Jay Leno impression. But this would be an example of like a sequence diagram where you're showing which part of the system is active at any one time. You're showing the sequences of events as they occur and what part of the system is being utilized. So this looks particularly complicated, but you can do them quite a bit more simply. You know, here's an example of, you know, an online bookshop and a web customer using it. They search inventory until they either view a book description or add it to the shopping cart, and then they can go to checkout. You know, here's one for a Facebook authorization type server, things like that. Oops, you're not seeing all of this very well. And the web link for this, of course, is in the slides, which you can see. You can see the link to on the 3240 website. The next is the activity diagram. So the key with sequence diagram, though, is we're very much focusing on like the passage of time, where time goes from top to bottom. An activity diagram is more like a flowchart. So something like you start at a particular point. You start from there. So you typically start, there's a black circle that indicates this is where you enter. From there you can either search, browse, whatever. You search for an item. If the item is found, you can view it. If the item is not found, you return back to the search screen. You can browse items, again, similar idea. But this is more or less just a glorified flowchart. Decision points are diamonds. Events are these ovals. And we eventually exit the system through these sinks, which look similar to the starting point, but there's a white outline. So this is an example of an activity diagram. Of course, the website we linked has a few more. Definitely encourage you to take a look. So that's activity diagrams. From there, we're going to spend most of the rest of this time talking about class diagrams. And a class diagram is how we model the classes in the system. For example, say we were to do some type of course enrollment system. We might need, we need student objects, which have a list of courses. The students have a set of enrollments, that is a set of courses they're enrolled in. From there, they enroll in a particular seminar, which is taught by a professor, etc. This is how we could outline the class. I have another example later. And the idea is we want to break the system down into the classes that we are going to have. And this can be classes and any of their relationships. So that is whether or not they have subtypes or whether or not they have associations. With subtypes, we're talking about that OO hierarchy, things like inheritance, interfaces, abstract classes, etc. And so each of these boxes represents a particular class. If that class is abstract, we would denote it with something like this. We list the attributes, that is the fields, as well as their visibility, public, private, protected. We state their operations, that is the functions, the methods, as well as their parameters, their return types, and their visibility. And visibility is denoted with plus for public, minus for private, and # for protected. And there's 6 different types of arrows, although we're really just focusing on a few. So there's inheritance, which is a line with a white triangle. And similar to inheritance is realization or implementation. The difference between the two, you realize an interface or realize an abstract class, whereas you inherit from an existing class. So if we're talking an abstract class or an interface, you use a dotted line. If you're talking about a class that can separately be instantiated, so not an abstract class that you're extending, we use an arrow. And the arrow points from the child class to the parent class. Similarly, we have, so these two, so this is an is-a relationship. This is, an alarm clock is a clock and inherits from clock, for example. These two are a has-a relationship, so a car has a engine, a car has tires, and they're slightly different, but they both refer to this thing has this class has multiple instances or one instance of this other class. And then dependency, which I spelled amazingly well, frankly. Dependency is just a uses relationship. Similarly, there's association, which is similar to dependency, and in fact, you may often see people use association for dependency. But an association is when two classes potentially are acting together, but it's not explicitly one class is using another. From there, with aggregation, composition, association, we will often identify the multiplicity. And what I mean by that is the following. Here is a UML class diagram for an online shopping system. The customer has 0 or more orders. 0 ... That means 0 or more. And that's because a customer may not have any orders, right? Their orders may all be resolved, so they don't have any right now. They can make multiple, they can make one, whatever. They can have any number of orders. But the customer object is going to be associated with multiple orders. Each order is going to have one or more order detail objects, and each order detail is associated with exactly one order. So notice when I say order has a or has one or more order details, the diamond is on the side of the owner. The order owns the order detail. So the diamond is on the side of the thing that possesses the other. So if I say a car has 4 tires, the diamond would be on the car side. Similarly, with payment methods, we have 3 different ways that is implemented. They all inherit from payment, and cash inherits from payment, check inherits from payment, credit inherits from payment. And each order has one or more payment, and each payment is associated with exactly one order. Also, each order associated with exactly one customer. So this is a useful UML diagram. Again, look at the class examples that we have in the link. That will certainly help you out. So when we're laying out a class, the attributes go in the mid. The class title obviously goes at the top, book. The attributes go in the middle, so this is private title string. And then the functions in the bottom, or the behaviors, borrow, C, which is data type copy, void. This is the variable name C and the data type of the input, which in this case is data type copy. And it returns a void. Copies on the shelf, that's how many books you have on the shelf. That's going to return an integer, a number. Get title, return a string. With nothing, if you don't list anything, that's going to typically be the class default. In Java, that is package protected. But generally, you should always pretty much use plus, minus, or when needed, protected. So when we're talking about objects, we think of them as kind of real-world objects. And is there a connection between them? And they can be associated, or there can be a dependency in multiple ways. For example, if A sends a message to B, that is an association. If object A creates an instance of B, but doesn't own it, it's very important because, you know, if like a car has a tire, it owns tires. But this is specifically A creates an instance, but it doesn't possess that instance. That's an association. If there's an object of class A that has an attribute type B or collection type B's, this is getting into aggregation here, but that is also a connection. Or an object of class A receives a message, that is, a function is called that passes in some instance B, but that's only an association if A explicitly uses B. If A doesn't use B and it's kind of just a pass-through, that's not really an association. So again, we've talked about inheritance. With inheritance, there's two different kinds. Either you're inheriting from a parent class, or you're implementing an abstract class or an interface. And for those, we use respectively inheritance or realization. Aggregation and composition, these are both has-a relationships, but the best example that I can come up with, let's imagine we had a company object that has a set of people objects. If the company ceased to exist, the people who work there would still exist. They are separable from the company. Those entities do not require the company to exist. If you take a tire off a car, the tire doesn't disappear. It still exists. You could put it on another car if you wanted. So that is aggregation. It gathers things that exist independent of it. A company, however, has a set of accounts. And if the company ceases to do business, those accounts cease to exist. So that is aggregation. Or, sorry, that is composition, excuse me. Aggregation is when the entities can exist separate from the owner. Composition is when the whole, the company, is unseparable really from the accounts. So the accounts are unseparable from the company. So again, this link here, definitely check it out. Give it a read. Consider that required reading. So from there, on Thursday, we will do a design decomposition practice. So we'll talk about that then. But otherwise, that is the video. Definitely give those links a read, especially this one. And we will see you next time, everyone. Take care, and thank you so much for watching.